Before we get started, I'm located here at the University of Massachusetts Amherst, which I'm happy to say acknowledges that it was founded and built on the unceded homelands of the Pocumtuck Nation. And I also, before I got started, wanted to also say that I feel very privileged to be presenting the work that I'm presenting to you today, which has been a culmination of work over the last 10 years. Today, we'll really focus on the work that we're doing in our lab now. But this work has been kind of leading up to this, and it's taken place over 3 different countries, Canada, the UK, and now the US. And no matter where I've been living in the world, there've always been people struggling with potable water equity. Right now in the US, there's a big drive to get rid of this work and the funding that is used to bring ourselves closer to a place of global water equity. And just in the last several weeks, the funding landscape has been somewhat decimated. So I just want to give some thoughts to US researchers, if there's any in attendance today, who are feeling these effects and feeling uncertain about whether we can continue on with this type of work. But also just want to implore people, especially those in Canada, to keep doing the good work despite the speed bumps that we're feeling here south of the 49th parallel. So with those kind of preliminary thoughts, I'll jump into to my presentation. And since it's WASH Canada, why not give a Canadian example? So this should be familiar to everyone, and this is obviously a map of Canada. And as we look around from province to province, you'll see a kettle with a number, and the number is the amount of drinking water advisories in each of these provinces. So this could be boil water advisories, water quality advisories, or do not consume orders. And if we use British Columbia as an example, where UVic is, we'll see that there's much more boil water advisories, or I should say drinking water advisories, than any of the other provinces. So there's a few reasons for this, but if we just think about the geography of British Columbia, we see that there's a lot of small communities that might be located on the coast that are only accessible by 1 or more ferries, or perhaps no ferries at all, right? You just need a boat or a plane. We have the Rocky Mountains and all sorts of communities nestled in and around the Rocky Mountains, as well as other mountain ranges. That makes it hard to access during certain times of the year. And then some communities that are very accessible or somewhat accessible during some parts of the year become very inaccessible during other parts of the year. So this is around Prince George, and there's actually a small house under that big pile of snow there. And at least traditionally, British Columbia hasn't been thought of as a place where water is scarce. Although my last few years of living in British Columbia, and that was probably about 10 years ago, in the summers, there were water advisories in Metro Vancouver, but that was more so for things like watering your lawn. But if you start to look into the data of where these drinking water advisories predominate, you start to see a pattern. And communities that are small, or communities that are remote, or indigenous communities seem to be more susceptible to these water hardships. And there's several reasons for that. There's societal variables, and there's technological variables, amongst other things. And the technological variables are the things that myself and my lab think about a lot. And I'll give a couple of examples of that. So for remote systems, you need, with conventional water treatment, you need a constant chemical supply chain and a constant energy supply chain. So there's still many communities, remote communities in British Columbia, that are only accessible by boat or by plane. So to get processed chemicals there regularly and consistently can be problematic. There's also many communities who aren't connected to a kind of central energy grid. So they might be running on diesel generators, for example. And obviously these challenges aren't limited to Canada, and they're a global problem. And that's why these WASH talks exist. When I moved to the United States in 2021, I wanted to look into these problems or these water hardships that may or may not exist in the United States. So in 2021, the EPA, the Environmental Protection Association, said that over 1,000 communities were in serious violation of the Safe Drinking Water Act, with an additional 21,000 or over 21,000 in significant noncompliance with wastewater. If you start to look at the data of where these violations and water hardships and noncompliances are, you see that they predominate in or are associated with things like rurality, indigeneity, poverty, age, education. Even here in Massachusetts, we work a lot with disadvantaged communities, which also suffer from elevated water hardships. Obviously, we can keep zooming outside of North America, and we see that safely managed drinking water services are lacking globally. And 8 out of 10 people who lack basic services were found to have lived in rural areas, with half of those living in, quote, the least developed countries. So if we wanted to achieve the WHO and UNICEF goals of universal access to safely managed water services by 2030, the progress in which we are going would need to be multiplied by 4. So now getting more specifically into how this relates to the work that we do in our lab. If we think about a conventional water treatment process and try and diagnose where these conventional treatment options don't necessarily work for, say, a remote community or a small community, and then we can think back again about these technological variables like a constant chemical supply chain. There's many conventional systems that require a constant chemical supply chain, namely coagulation and flocculation, as well as disinfection, whereby with coagulation and flocculation, you need to be providing coagulant to a community, or with disinfection, something like chlorine, for example, and chlorine being one of the most ubiquitously used oxidants for the disinfection of water. Historically, engineers have innovated economical and reliable ways to mass manufacture commodities and chemicals, for example, that enable our modern society, like water treatment. And these processes have typically involved mining exhaustible resources and releasing enormous amounts of waste into the air and water. For example, water and wastewater utilities account for about 5% of the global greenhouse gas emissions, of which 70% is caused by wastewater treatment. And this doesn't even consider the 80% of wastewater that is released into the environment without any treatment at all. So if we think about current and conventional water and wastewater treatment, we have our chemical supply chain coming into our treatment plant. We have our energy supply chain coming into our treatment plant. Our water treatment works is consuming chemicals and they're consuming energy, which leads to emissions and leads to waste. If we want to think of a kind of modern example of waste from a drinking water treatment plant, with the new EPA rules on PFAS, most PFAS or accepted PFAS treatments are not destruction techniques, but physical removal techniques. So we're concentrating these and then we're sending them off to a landfill, for example, where inevitably our leachates will somehow make it back into our waters. One other thing that I want you to think about that could be problematic with conventional water systems is the idea that we need to send our water samples off to a lab to be tested, right? And lab testing is very expensive. So we send it to a lab to see how much PFAS we have in our water, in our raw water, in our treated water. And you're looking at kind of $250 to as high as $500 US to get a sample analyzed. And obviously, the more emissions we produce and the more waste we produce can make it back into our water supply, making this whole cycle a lot more challenging for the future. So what we're trying to do in our lab is having more of a circular water system. So I think that shifting towards chemical manufacturing processes that are more inherently sustainable and circular, trying to integrate environmental engineering principles into kind of traditional chemical engineering design and fundamentals. So what we do is we're trying to lead this transition of chemical manufacturing, whereby we can synthesize our chemicals on site. We might be able to generate energy on site, where we don't have to send off samples for water quality monitoring. We can do that on site and use that to both inform and optimize processes. So another thing that I haven't mentioned with remote systems is kind of the hardship on water operators. So unlike a system like Metrovan that has a large team of water operators that help make the system run, when you get to these small communities or remote communities, it might just be one person who's kind of on call 24/7, and a lot of stress and responsibility is put onto one person who might have another job, right? This might not be their main job. So today, I want to go over a couple of examples of what we're doing in our lab. I wish I had an hour and a half or 2 hours with you all that I could go over all the projects, but I picked a couple that might be of interest. And that relates to both material development, so chemical synthesis, on-site chemical synthesis, as well as developing of sensors for water quality monitoring. And I'll get into examples of both of those. Before I got into that, I just wanted to show a couple pictures of some of the research that I did when I was in British Columbia. And this is kind of, I thought it was nice because it shows where my love for research and my love for working with remote communities began. So I was a master's student at UBC, where I was scaling up an electrochemical system that produces coagulant chemicals on site. And I got to pilot this at 2 remote communities and evaluate its ability to remove organic matter, so natural organic matter, as well as metals like arsenic, iron, and manganese. So this is kind of where it all began for me. And not only my love for research, but my love for electrochemistry. And you'll see a lot of what I do is electrochemically focused. All right, so first off, on-site chemical synthesis and pollutant degradation. So for those who aren't familiar with electrochemistry, I'll try and give kind of a chemistry or electrochemistry 101. And let's imagine this beaker full of water, and this is the water that we are going to consume, say, or drink. And you have an electrochemical cell in the water. And an electrochemical cell can consist of 2 or more electrodes. One is your anode, where your positive charge is, and one is your cathode, where your negative charge is. And you might have a power supply here, right, for an electrolysis cell. And if you have a power supply, you can turn it on, and you can start to force electrons to flow through our electrochemical cells. So this is a current. When you have things in your water, like ions, for example, if we think about chloride, if we had chloride in our water, that chloride would diffuse to the electrode surface, and some reaction would take place to then make chlorine. Chlorine being, I mentioned before, one of the most ubiquitously used oxidants or disinfectants that we use in water treatment, and one of the most significant public health outcomes of the 20th century. We can think about kind of more unique reactions that could be happening. So for example, if we had iron in our water, which a lot of groundwaters have, that iron cation could diffuse to the electrode surface, and you could make what is called ferrate, so an iron 6+ cation. And ferrate's a very strong oxidant as well. It's looked at a lot for drinking water treatment because it doesn't form disinfection byproducts like chlorine does. It also functions well as a coagulant once it's been reduced. It hasn't made its its way into the water treatment space yet, but it is used in wastewater treatment as well as industrial waste. Obviously, there's a lot of other reactions that can be taking place. So if we think first about our ferrite example, our iron example, and we think about the pHs that we would have for drinking water, which would be in the circumneutral pHs. So let's say anywhere between 6 and 8. And we look at where ferrite predominates in an electrochemical system, we see that we have to increase our potential quite high. So kind of in the 1.2 volts to 2 volts is where our ferrites are stable. The problem is with electrochemistry, the thing that is surrounding your electrode predominantly is water, right? Water is all over our electrode surface, and water also likes to react with our electrodes. And water reacts to make oxygen. So we'll make hydroxide and oxygen. So any effect or any possibility of actually making ferrite is overpowered by oxygen using kind of standard metal electrodes. So with kind of standard electrode materials, our oxygen evolution reaction onset potential, the potential, electrical potential at which this starts, is at 0.8 volts. However, in recent years, people have been making these advanced materials that have greatly increased our potential window. So using what are called BDDs, or boron doped diamond electrodes, we can increase that potential window quite a bit before we start making oxygen, which gives us a lot more space to then have the potential synthesis of ferrite. So how does this fit into what we're doing in our lab? So one example that I'll show you today is the synthesis of chlorine. And I've mentioned chlorine a few times now, but how can we make chlorine evolution on site at a water treatment, say a remote water treatment system, instead of having to truck in or train in hypochlorite or chlorine? It's worth mentioning that currently about 90% of all chlorine, whether it's for water treatment or pulp and paper processes, are made electrochemically. The problem with it is that the kind of gold standard electrode involves platinum group metals. So metals like platinum, iridium, and ruthenium, which make it a very expensive process, both from a capital expenditure as well as an operational expenditure, because these electrodes don't last forever. So what we have been doing in our lab is looking for alternatives to make very cheap electrodes that smaller systems could use to make chlorine on site, instead of relying on this decentralized or this centralized model of you have your chlorine plant and you truck your chlorine on site and you store it and use it as needed. So we've been looking at cobalt antimonate. So that's using cobalt and antimony instead of platinum group metals like platinum and ruthenium. And just an example here for raw costs of antimony and cobalt is about $6 per pound and $20 per pound respectively. Whereas with materials like iridium, it gets into the tens of thousands of dollars per pound. How do we do this? So we have a substrate material, like a titanium plate, and then we put all of our cobalt and our antimony, we dissolve it in water, and we electrochemically deposit it on our titanium electrode or substrate. And then we take that and we put it in the oven and we anneal it. So kind of a fancy word for crystallizing it on the electrode surface. From there, we can do a bunch of science with it, like looking at it under a scanning electron microscope and energy dispersive X-ray spectroscopy. So that's SEM EDS, and that tells us the elemental abundance and surface stoichiometry and morphology. So how our antimony spread out over the surface, or how our cobalt spread out over the surface. We can use things like XPS, or X-ray photoelectron spectroscopy, and this will tell us the electronic states and elemental composition. And then we've also been doing things like scanning electron microscopy, or SECM. And this is telling us specifically on certain locations how well our material, our synthesized material, is doing at making in this case, chlorine rather than oxygen, for example, or any unwanted chlorine species that might be present, like chlorite or chlorate or perchlorate. So by looking at all these different generation parameters that we can change, like how much cobalt we put in the solution or how much antimony or how long we deposit it for or the pH that we use, we can get all these different materials that we evaluate using all these different analytical techniques. But really the main one, and the one that is of interest to us, is understanding how much chlorine we actually make. So here is a graph of our best performing and our worst performing cobalt antimony electrode, our best performing in blue, our worst performing in black. And this was after a bunch of initial kind of scoping experiments. And then you see here this gold or this yellow line is our ruthenium iridium electrode. So we got this electrode off the shelf from one of the main chlorine electrode manufacturers in the world. So this gold one was a specific electrode that's used in chloralkali processes. And you can see that our electrodes were exceeding that of kind of the gold standard of chloralkali processes. Another way of looking at this, because I was mentioning, well, some of our electrical currents going to making chlorine, but some also might be going to making oxygen. So a nice way of understanding this is something called Faraday efficiency or current efficiency. And that's just telling us the percent of power we're putting into the system. What is the percent that's actually going towards making chlorine? And you can see that, again, our top performing electrode operates at about 55% on average. So about 50% of the power, 55% of the power that we're putting into the system goes towards making chlorine. So obviously we'd like it to be at 100%, and we've been working and still continue to work on improving that. And some of the techniques that we're using to do that is using machine learning. So developing machine learning models to predict how we can go back into the lab and change our conditions to maximize catalytic activity and electrochemical surface area for better chlorine production. And this is just an example of a Gaussian process regression model that we used. And we basically, all this data in blue, we used to make our machine learning model that then informed us on specific generation conditions. And then we made that electrode that our model said would be good. And we tested it. We can see that, yes, the current efficiency increased a little bit. So we're continuing on with this work, and we're trying to make it more sophisticated and trying to use more data. And this is really a nice way of not indiscriminately doing lab work, right? Lab work is inherently very wasteful. Every one of these data points that we produce, we've made a lot of reagent materials filled with cobalt, filled with antimony, and then we make a lot of waste when we're analyzing our chlorine evolution. And then when we're annealing it, right, we're using 600 degrees C, so we have to use a big oven, which takes up a lot of energy. So what we're trying to do now is use the data that we have, whether that be through our SEM images, our scanning electron microscope images here, which tell us about morphology, or our EDS images. You can see how our SEM images match with our EDS images, and this is telling us how cobalt is distributed on the electrode surface or how antimony is distributed along the electrode surface. And we're trying to use more advanced machine learning techniques like convolutional neural networks to take these images and give us useful information from them. Things like optimized synthesis parameters. So can our convolutional neural network models tell us about how to maximize our electrochemical surface area, or what our best cobalt to antimony ratio is? Can we use informed physics, kind of fundamental electrochemical equations to better refine our neural network models or target specific reactions? So in addition to things like chlorine evolution, we're looking at using these models. And in addition to kind of supervised models using the data we get, using unsupervised models and simulation techniques, chemical simulation techniques to target specific reactions. So we're not bound to the boundaries that we've given our model. So things like PFAS degradation is of interest to us, and we're hoping to use chemical simulation models as well as these neural network models. So if we think about this same process that we've been using to react chloride to form chlorine, we can also think about it for reacting with our pollutants directly in water, and this is called electrooxidation. So by the same principle, we have our electrochemical cell in water. We provide some current to that cell, and we might have some pollutant in solution. And if that pollutant, like the chloride, makes its way to the electrode surface, we can oxidize it to form byproducts or continuously degrade a pollutant to complete combustion if it's an organic pollutant. And this can happen two ways: through direct oxidation, whereby there's an electron transfer between our pollutant and our electrode surface, or it can happen through advanced oxidation. So again, we have water on our electrode surface. It reacts with our electrode to form hydroxyl radicals. And again, we want to not make oxygen. If we can make hydroxyl radicals instead of oxygen, then these hydroxyl radicals end up reacting with our pollutants. So obviously these can happen simultaneously, right? If we have some pollutant, in this case, for example, atrazine, which is a ubiquitous pollutant, it's a pesticide. When I was in the UK, atrazine wasn't such a huge subject because it has been banned in the EU for quite some time. But in North America and the US, atrazine, I read a paper where it was a national sampling campaign, and as much as I think just over 80% of all riverways had some amounts of atrazine in it. So, or not necessarily just rivers, but surface water sources. So if we have our atrazine that diffuses to our electrode surface, it could react with our hydroxyl radical. It could react directly on our electrode surface, and any of its byproducts could also, again, react with hydroxyl radicals or our electrode surface and continue to be degraded until complete combustion. So at that point, you only have CO2. Or if we have iron in our water, which many groundwaters have, that iron would also be reacting with our electrode surface to make our ferrates, which we thought about before, which are more stable than hydroxyl radicals. So they can diffuse out to the bulk water solution and start to react with atrazine that hasn't made its way to the electrode surface. So it can happen through kind of a simultaneous processes like this. You can imagine if we had chloride in our water, we would also be making chlorine. So I'll show you one slide of results of that which we did with PFOS, which is one of these legacy PFAS, long-chain PFAS species. So the light gray line here is the electrochemical degradation of PFOS with no iron in the water. And as small amounts of iron were present in our water, we could see that our degradation of PFOS increased. So our first order reaction rate constants increased quite a bit. And so this was published in a paper. And there's another paper that talks about this ferrate formation and its usefulness in kind of real water samples. So we're using iron levels that are typical of groundwaters and understanding how this can help increase degradation rates of common and ubiquitous micropollutants in water. Okay, so shifting towards electrochemical sensors and water quality. I'll just say one more thing about this. So we're continuing this work on a number of different pollutants, including PFAS as well as textile dyes, which I'll briefly talk about in a little bit. So electrochemical sensors. So water treatment only works if resources and personnel are available. And we've kind of touched on this a little bit already, but it relies on a team of skilled operators and personnel, as well as a plethora of resources in order for it to be successful, right? This involves big budgets, especially for big centralized water treatment systems. If you think about systems like Metro Vancouver, It involves continuous contaminant monitoring, right? We want to know how much natural organic matter is going into our system. We're not only monitoring pollutants as they go through the treatment system, but kind of our raw water quality monitoring. But these centralized approaches are, but these are for centralized approaches where these resources are available. So what about a town that isn't testing for water quality? Or what if you grew up drinking water on a personal well, like I did for the first 18 years of my life, where we had no treatment at all? A lot of the world relies on water from wells that are untreated. So how would you go about getting your water tested? Well, you can take a sample and send it to a certified lab, but this is really expensive and time consuming. So I don't know if anyone's ever sent a sample away to a lab, but say if you wanted a heavy metals analysis done on your well water, you would take a sample, you would send it off to a lab, and at that point, it would be somewhere on the order of a couple $100. If you're looking for PFAS, it might be $300, $400 for a single sample. And the other thing to think about is even if you are on a centralized system, what about contaminants that aren't treated at the treatment system? And one contaminant that this happens with is lead. Lead is something that could greatly benefit from on-site sensors because lead is a bit of a unique contaminant in that it enters our drinking water treatment our drinking water system after treatment. So your water's treated. If you're lucky enough to have drinking water treatment, it goes into your distribution system, into your pipes, but it's your pipes that slowly leach lead into the water. So leaching into the water from service lines, which up to about 40 years ago contained some amount of lead, if not in your service lines, in the soldered fixtures when you're connecting metal pipes. Where I live now in the Northeast in Massachusetts, essentially any home built before 1979 has a lead service line. Lead is a ubiquitous contaminant of concern, so much so that whenever I give a presentation and talk about our sensors, I can just kind of Google the city name and say lead and water and put that in Google and press the news tab. So I did that and I put in, I Googled Vancouver Island lead drinking water. And this story came up in the Times Colonist just 3 weeks ago, or I guess 4 weeks ago now. High levels of lead found in water in Port Alberni city facilities. So Port Alberni's treating their water. They're sending their clean water out, but once it makes it to the user, they have lead in their water. So what should Port Alberni do? They could start digging up all their infrastructure built before the 80s or 70s, start ripping out the plumbing in their old buildings. But this would be a millions of dollars endeavor. And lead's not just a North America problem, it's a global problem. It's one of the contaminants of concerns with the WHO. And it's kind of ubiquitously found in wells and pumps, hand pumps, for example. Lead, some amount of lead is in metals of hand pumps. So how do we know as someone drinking water whether our water is safe to use? Again, we could send it off to a centralized lab, but that is kind of a privilege to be able to do that. If we sent it off to a lab, we would have to send it to a lab where they have the advanced analytical techniques. So they use something called inductively coupled plasma mass spectroscopy, or optical emission spectroscopy, mass spectroscopy. So that's ICP-MS or ICP-OES. And this can take hours if you're lucky, or days more likely. So what we're trying to do is to develop sensitive sensors, and in particular that combine multi-analyte sensors like copper and lead, for example, that can be used at the point of use. So these are kind of point of sampling. If you were to take your water sample at your tap, you could do your analysis right there, or something that's built right into your tap right away. So if we take the example of both copper and lead, and one thing I should say about copper and lead, this leaching happens during times of stagnancy, right? So overnight, you take your last shower, you go to bed, and when the water is not being used, lead and copper slowly dissolve into your water. So when you wake up in the morning, you go to take a drink of water, and that's when your lead and copper levels are highest. So if we were to be able to make a sensor that fits in at your point of use, your tap, that's constantly in real time detecting lead. So you go to flush your water and your sensor's telling you, okay, lead levels are decreasing, copper levels are decreasing. Okay, now it's safe to drink your water. And the ultimate goal would be to use that sensor data to then incorporate feedback process controls. So if you had decentralized water treatment, it would go back and help inform water treatment kind of downstream of your tap. I should say that this work is in collaboration with Fraunhofer USA. So this is a material research organization based out of Michigan, and they create all the materials that we use for this. So how does this work? You can imagine your electrode, no different than kind of the electrochemical setup that I showed you before, where you have, actually in this case, you have 3 electrodes, but we're just thinking about our one specific sensor electrode, which we call our working electrode. And if you want to picture what this looks like, it's kind of a round electrode. So it's this black part here, and its diameter is about 2 millimeters, so very, very tiny. And we put this in our water. And if we have lead in our water, which is a positively charged ion, so a cation, what we can do is for some amount of time, induce a negative potential on our electrode surface. So if we have a negatively charged electrode surface and we have our positively charged cations, whether they be lead in this example or copper, what ends up happening is that our lead gets attracted to our negatively charged surface and it absorbs to the surface. So at this point, we can start increasing our potential. And at a certain point, the potential is going to increase so much that our lead is going to want to leave our electrode surface. And it's that point where we get a bit of a current response. So if we are increasing and controlling our potential and increasing it and measuring the electrical current response, we get this kind of peak here that happens. This process is called anodic stripping voltammetry and differential pulse voltammetry. If Alana is on, my grad student working on this is on the call right now, I'm making it seem much more simple than it is, but we'll keep it at a high level right now. So we use anodic stripping voltammetry and differential pulse voltammetry, and we get this peak. And what we can do is measure this peak, both its intensity in current response as well as its area, so the area under the curve. So anyone doing chromatography, for example, on the call will know with chromatography or mass spectrometry, we take the area under the curve, and this has some relationship to the concentration of, in this case, lead that was absorbed to our surface. So we can make this calibration curve where we put specific amounts and known amounts of lead into our water. We run our ASV DPV, which is our anodic stripping voltammetry and differential pulse voltammetry, and we get an area, and we can plot our peak area versus our known lead concentrations. And what we hope to get is this nice linear line whereby our lead concentrations have a linear response or a linear relationship to our peak area response. So this is some work that we did in the lab, and we do get a nice linear line. From this experiment, we are getting limits of detection at around 5 ppb and limits of quantification of about 15 ppb. So for EPA, there's a 0 lead and copper rule, but the kind of maximum concentration levels, allowable concentration levels, is 15 ppb. So from a kind of federal governing standpoint, systems need to be under 15 ppb. So our limits of detection are right around those EPA MCLs, which is great. Some hiccups that we're having is just the consistency of getting this nice calibration curve, but these are things ongoing work that we're currently doing. We're also working with Fraunhofer to look at these kind of novel electrode setups. And so this here is one of these setups where on a silicone wafer, Fraunhofer has printed all three of our electrodes. So here we have our reference electrode, and this is the electrode that's measuring our potential response. This is our working electrode. So this circle here is our actual sensor. And then this is our counter electrode. So this is what's providing that kind of circuit. These are our two electrodes that we were looking at before in that kind of animation that I showed. You can see that this wafer is very small, right? So less than a centimeter wide and about 1.5 centimeters long. It's on a flat surface, so it'd be very easy to incorporate something of this size into a point of use, or into a small kind of modular sensor that you could take out into the field. If you're going on site to a community where you had to take a water sample, you could put this small little wafer in the water and quantify your lead levels. So again, this is ongoing work. We're trying to look at lead and copper mainly, but we're also thinking about other contaminants of concern, things like lithium, cadmium, nickel, manganese, iron. Arsenic would be wonderful. Arsenic and manganese are tough because they're very low potentials and very high potentials, where we're wrestling with our oxygen evolution reaction, which I mentioned before as well. If you kept going up, you'd have the same problem with hydrogen generation. All right, so at this point, I want to recognize the people who are actually doing the works. So this is the current lab. Shane, I included here. He graduated last semester, but he did a lot of the chlorine work and some of that initial machine learning work. So I wanted to include him as a current lab member, but he's off in industry working now. We have Alana, who's working on the lead and copper sensors. Faye, who I didn't showcase any of her work, but I showcased some similar work where we're using electrochemistry to degrade pollutants. So Faye's using electrochemistry to degrade textile dyes, and textile dyes account for a huge amount of the overall wastewater that's produced in the world. So a lot of countries that have a lot of textile industries, their waters are heavily polluted with textiles. And in addition to that, looking at when we degrade them, are we making disinfection byproducts? Lohita, a PhD candidate in the lab, is looking at electrochemical activated carbon for these decentralized approaches. So I didn't get to showcase it, but this is a really cool project as well. So we use activated carbon in conventional water treatment, but this is something that we need to change out. Once you've reached your capacity limits of your activated carbon, you need to send it off-site to be thermally regenerated. So Lohita is working on an electrochemical activated carbon where we can use electrochemistry to speed up the kinetics, how fast things absorb to the surface, as well as regenerating it on site using electrochemistry, so we don't have to send the GAC off to be thermally regenerated. The newest member of our lab, Hiroki, he's really going to be diving into the machine learning and computational simulations for the material development. So that could be material development for chlorine evolution or for PFAS degradation, or for any electrochemical. It could even be for new novel materials for our sensors. And then Kieran is kind of the analytical instrument and characterization guru of our lab. He does a lot of work with our mass spec, some more novel analytical instruments that we've been developing with Shimadzu that looks at how we can characterize organic matter better. So we can understand how to treat it or what the consequences of treatment might be on disinfection byproduct formation. And with that, I guess just kind of final thoughts are the goals of our lab, which I kind of briefly outlined at the start, but we really want to make these kind of modular systems that are accessible to all, that don't rely on a constant energy supply chain, that can actually produce energy, right? So another project that we had last year was producing hydrogen while we were treating water. So on one side, we're oxidizing and degrading pollutants, but on our cathode side, we're actually making hydrogen. So can we use that hydrogen to blend with natural gas to bring down the overall costs of our treatment and overall need for external energy? Developing sensors that can help inform and automate treatment, so we're not always relying on a water operator who can't always be there 24/7. And the pie in the sky idea is to have these kind of standalone systems that can be very easy to operate and that don't require a lot of energy to use. So with that, I want to thank all the organizers of the WASH Canada and the WASH Talk series. Again, I said it on the first slide, I'm very honored to be invited and to be able to speak to you all today, and I'd be happy to answer any questions that people might have.